Okay, let's continue our discussion. Today we are going to discuss example 5.8. And what is given here? To simulate car accidents, auto manufacturers study the collisions of moving car with mounted springs of different spring constants. Consider a typical simulation with a car of mass 1000 kg moving with a speed of 18 km per hour on a smooth road and colliding with a horizontally mounted spring of a spring constant 5.25 into 10 raised to the power 3 Newton per meter. What is the maximum compression of the spring? Okay, let me draw the situation for you. So what is happening here? Let's say here you have a spring, and let's say something here just to block the car, and this is the car. So initially this car is moving, and yes, mass is given. So mass of this car is 1000 kg. And now if it is moving with a velocity, and velocity is 18 kilometer per hour. So it is moving with a velocity, I think constant velocity, not changing one. Okay. So it is moving with a constant velocity 18 kilometer per hour. Okay. So what will be the kinetic energy possessed by this car? This will be kinetic energy possessed by this car will be 1 by 2 times mass times square of velocity. And it will be easier if we keep all the things in SI system. So let us change this velocity 18 kilometer per hour into meter per second. So how can we change this? 18 kilometer, that is 18 into 1000 meter divided by hour. Hour is 3600 seconds. So now it will be in meter per second. And I think it will be, let me start from here. So 2 and then it will be 5. So velocity will be 5 meter per second. Then kinetic energy will be 1 by 2 into 1000 into 5 into 5. Okay, so this will be how much? 25, and into 1000, 25,000 divided by 2. And I guess it should be 12,500, and it is energy and everything is in SI system, so it should be in joule. Okay, now moving to the next point. What is happening next is this car is being collided to this spring, and then there will be compression. Obviously there will be compression, and if this spring is sufficient enough to hold this car, there will be some point where the maximum compression will occur, and after that there is no further compression. So let's say that displacement of this end of a spring is xm, and for that much compression this spring force should do certain work, and that work will be, we already know that it will be, let's write w, because of the spring force. This will be minus k times x m square divided by 2, and then it will be, okay, let me check what is the value of k. K is 5.25 into 10 to the power 3 Newton per meter. So 5.25 into 10 to the power 3 Newton per meter. Okay, I will write because this is work. So at the end, all these units are going to give us a final unit joule. So we are not bothering about those things right now. Okay, x square. This one we have to find out, this xm, and divided by 2. And what is happening here? This car has some kinetic energy, and finally this car comes to rest, that this car is going to do an energy transfer of 12,500 joule. Initially it has kinetic energy of this much joule, and finally when it stops, this entire kinetic energy is going to give rise potential energy in this compressed spring, and that potential energy will be equal to the negative of this work done by this spring force. So based on that fact, we can write this work done should be minus of, sorry, minus 1200, 12,500 joule. And then Here we have, and this will be minus 5.25 into 10 to the power 3 into x m square by 2. Now you can calculate and you can get what is the value of xm. Let me do it somewhere else, and then, or I can write directly what is the answer here. Okay, let me check it. So you will get here maximum compression of 2 meters. Okay, you can solve this uh, thing to get xm, and there should be no confusion about this. How I have equated this minus kx m square by 2 to this value, because at the end the spring will get this much energy from that moving car, and it should be equal. The potential energy raised in this spring should be equal to the work done by this colliding car. Okay, now, okay, it has been done.